Have you ever wondered how an AI looks at a photo with a dozen possibilities and just knows? How it can confidently point to one thing and say, yep, that's a cat. Well, the secret behind that confidence, a lot of the time, is a powerful little function called Softmax. Today, we're going to pull back the curtain and see how this one idea is a cornerstone of how AI makes decisions.
So let's start with the basic problem every single classification model has to solve. It looks at some data, right? Maybe an image, maybe some text, and its job is to make a clear choice from a list of possible answers. But how does it actually go from just a raw analysis to a final, confident decision?
Okay, so imagine our AI has looked at a picture, and this is what it spits out. These raw scores, which in the biz we call logits. Now you and I can look at this and see, sure, dog has the highest score. But what does 4.8 even mean? It's not a probability. These are just numbers. They're totally arbitrary. We need a way to turn this raw data into something that actually tells us how confident the model is.
So yeah, the challenge is pretty clear. We have this messy list of scores, and we need to transform them into a clean, understandable set of probabilities. Numbers that actually behave like probabilities should.
To do that, we need a function with a very specific set of skills. For starters, the outputs have to be positive, right? Because you can't have a negative probability. That makes no sense. Second, they all need to add up to exactly 1 or 100%. Third, and this is super important for training the AI, the process has to be smooth, what we call differentiable, no sudden jumps. And lastly, we really wanted to emphasize the winner. We wanted to look at the scores and amplify the differences, making it obvious which one is the front runner.
And the function that checks all of these boxes, the one that does everything on our wish list, well, that is the hero of our story today, the Softmax function. It is just a beautiful, elegant piece of math that solves our problem perfectly.
Now, I know the formula might look a little intimidating at first, but don't worry, it's actually pretty straightforward. All it's really saying is this. For any one score, you take e, that mathematical constant, and you raise it to the power of that score. Then, you just divide that result by the sum of all the scores after they've also been exponentiated. It's a clever two-step process.
Let's break that down. The first step is exponentiation. Using e to the power of x does two amazing things for us. One, it makes sure every output is positive. Two, it dramatically amplifies the bigger scores. That gap between a score of 2.0 and 4.8, after exponentiation, it becomes way, way bigger. The winner gets a huge boost. Then comes step 2, normalization. By taking each of those new amplified numbers and dividing them by the total sum, we basically force the final results to add up perfectly to 1. And just like that, we have a real probability distribution.
But just satisfying our wish list? That's only the beginning. The real genius, the absolute magic of Softmax, lies in two hidden properties that make it a total game changer for modern AI, especially when it comes to actually training these gigantic models.
But there's a potential disaster hiding in that first step. What happens if our model outputs a really big score, like 1,000? Well, if you try to calculate e to the power of 1,000, you get a number that is so astronomically huge, it literally breaks the computer. It can't store it. This is called a numerical overflow, and it would just crash the whole system.
I mean, that sounds like a deal breaker, doesn't it? How can we possibly use a function that seems so fragile? Well, it turns out Softmax has this incredible built-in defense mechanism against this exact problem. And that brings us to the first magic trick, a property called shift invariance. It's a fancy term for a simple idea. It means you can take any number you want, call it C, and subtract it from every single one of your scores before you run them through Softmax, and the final probabilities will be exactly the same. It doesn't change the answer one bit.
And the practical way we use this is with a clever technique called the log sum exp trick. To stop our computer from exploding, we just find the largest score in our list and subtract that number from all the other scores. This shifts all our numbers down so the biggest score is now 0, and e to the power of 0 is just 1. All the other exponents become tiny numbers between 0 and 1. The whole calculation is now totally stable, and we get the exact same final probabilities. Problem solved.
Okay, so that first trick was all about stability. This second magic trick is even more profound. It gets right to the very heart of how these models actually learn from their mistakes when they're being trained.
So when we train an AI, we need a way to tell it how wrong its predictions are. We use something called a loss function for that. And the perfect partner for Softmax is something called cross-entropy loss. Its goal is simple. It comes down hard on the model if the probability it gave to the correct answer was really low. It hates being wrong with confidence. And here,
Here is where the real magic happens. To teach the model, we need to do some calculus to figure out exactly how to adjust the scores. This is called finding the gradient. And when you combine the math of softmax with the math of cross-entropy loss, all the complicated bits just cancel each other out, and you're left with this beautifully, almost shockingly simple result.
So what does this mean? It means the instruction for how the model should learn is incredibly intuitive. The update signal is just the predicted probability minus the actual truth. So, if the model predicted 0.7 for the right answer, but the truth is 1, the error is negative 0.3. The model gets a clear signal, hey, you need to increase that score. It is the cleanest, most direct learning signal you could ever ask for.
All right, so with this super stable and elegant way of learning, let's go see how Softmax is actually used out in the wild. Its applications go way beyond just simple image classification. It's at the heart of some of the most advanced AI we have today.
One cool thing we can do is tweak the Softmax formula with something called a temperature parameter. Think of it like a confidence knob. A low temperature makes the model more picky and confident, pushing all the probability onto one winner. A high temperature flattens everything out, making the model less certain and its choices more diverse. This is absolutely critical for things like text generation, where you might want the AI to be creative instead of just giving the single most boring, predictable answer.
And what's really fascinating is that Softmax isn't just some random math trick somebody cooked up for AI. It's a fundamental pattern that shows up everywhere. In physics, it's called the Boltzmann distribution, connecting probability to energy states. In information theory, it represents the most unbiased, or maximum entropy, choice you can make given the data. And most importantly for us today, it is the absolute core of the attention mechanism, the engine that powers all the big transformer models, like ChatGPT.
Now you might be thinking, what about other functions like sigmoid? Well, the key difference is what kind of question you're asking. Softmax is for multi-class problems where there can only be one winner. It forces a competition. It's asking, which one of these options is it? The outputs are all connected. If one goes up, the others have to go down. Sigmoid, on the other hand, is for multi-label problems. It treats each output as a separate, independent yes or no question. Is a cat in the picture? Yes or no? Is a dog in the picture? Yes or no?
So if you take just one thing away from all of this, let it be this. Softmax takes raw scores, uses the power of exponents to amplify the winner, and then normalizes everything to create clean probabilities. And its perfect partnership with cross-entropy loss gives us that incredibly simple learning signal, your prediction minus the truth.
And this leaves us with a final thought to chew on. Softmax is absolutely brilliant at picking one winner from a competitive field. It finds the champion. But as AI tackles more and more complex problems, what happens when the best answer isn't a single entity, but a collaboration of many? What happens when we need teamwork instead of a sole champion? Well, that's a question that's driving the whole next wave of AI research.